So how do we define the wave nature of particles? So there are a number of ways how this can be done, where we take the classical equations from of mechanics and we apply the quantum concepts to them, and we can get the wave equation of the system. So one of the way how it is done is called the Schrodinger equation, Schrodinger wave equation. So basically, we what we are doing is we are taking the basic postulates here, which develop the wave equation, and it gives us the idea of how things will happen in uh, the waveform. So basic postulates of Schrodinger wave equation are that each particle in a physical system can be described by a wave function, right? So this is big psi, and you can see that there are it depends on not just three dimension but also the time, and it's space derivative, which means that in the 3D volume we would have a continuous finite and single valued derivative, which would be partial derivative of psi with respect to x plus partial derivative with respect to y plus partial derivative with respect to z. So in three dimension, how it changes would be written this way, and this function would be continuous finite and single valued, which means that there will not be any discontinuity and there will not be uh, any it would be defined at all the places. Now when we are dealing with the classical quantities, everyday quantities like energy and momentum, those have to be then translated into quantum mechanical operators. So the keyword here is, so we are taking the classical value and we are converting into classical operation on, and how it would be for taking from classical, and we are translating into quantum mechanical operators. And for now, if just remember, but later on we'll come and we'll see how do these make sense. So for x stays x, function of x stays function of x, the momentum is explained in terms of uh, the Planck's constant and partial derivative with respect to x. So since this was x, we are taking x here. If this was I, this would be, if this was y, this would be y here, and z as well. And energy is then dependent not on space but on time. So here again we have the Planck's constant, and J is the indicator of if you remember, there is real part and there is imaginary part. So this is the J operator, which is telling us we are talking about the imaginary part, and this is the partial derivative with respect to t. And in a similar way, this would be defined for them. Now these are for x direction, y and z would be defined in the same way. Now once you have this wave function defined, now we have to see the wave function and the probability of finding a particle which would have this wave function in a small volume, and that volume will be dx, dy, dz, and that is then defined as a function which now this is again probability density function, and this is of course sums up to be 1, and we are adding everything from minus infinity to plus infinity. The function, now this is the function which is calculated between the three contained volumes, and again this is the probability of finding that function, and this is the product of these two functions, the same wave function. But now the second part is which is showing in the small portions in three dimensions, x, y, z. Now we have to see that this psi is not multiplying. This is psi star, which is called complex conjugate. So we have psi and then we have psi star. And this is obtained by reversing the sign on each of the imaginary parts. So this is how we would define the probability of, let me just go back so we remove the writing. So basically we are taking the function, the wave function, and we are taking the complex conjugate of that wave function, both here. And then we are summing them over the volume, small volume dx dy dz, and the probability, the total of that probability is 1. Now, as before, we define the probability, then we take that probability and we find the average of that. Now, average value, we call, instead of psi, we call it, instead of the function x, we just call it q. Just like before, this would be complex conjugate of the wave function times the q operator. Now, what we are saying, because we are translating from simple classical f of x to now we are taking it into what we call quantum operator. So QOP is what we are calling as quantum operator. And similar like before, this is the average value of any variable in further related to the wave function. This variable can be again the position, the momentum, or the location. So if we think about it, what we are doing is we are, from the classical definition, we have just found the quantum mechanic related quantities, which ultimately will tell us exactly where is a wave located at any given time. Before we were talking about where is an electron located, or the probability of finding an electron, or the probability density function, because remember, we don't have discrete values, we have infinite values, so we need to find where is it located, so we take the density function. So that was in the classical particle way of looking at it, but the wave equivalent of looking at are these. So in the Schrodinger wave equation, or Schrodinger operators are, which give us these relationships. Now, if we find the wave function, if we know the wave function of a particle, we can calculate its average position, energy, and momentum within the limits of the uncertainty principle, right? So that uncertainty will stay there always. Now, the major effort then is in solving for the wave function within the conditions that are imposed by whatever physical system we are talking about. So, and that's this assumption that the probability density function is composed of the real part and the complex conjugate part. Or when we multiply them, we can write them as psi squared. So this is a complex function, which is another line of mathematics. Now, from these basic fundamental relationships, we can take the classical kinetic energy or classic potential energy or energy, and we can apply these operators, which we define, to find the wave equivalent of everything, whether that's energy, whether that's location. So that's where once we apply them, we get these quantities, which are nothing but the equivalents of kinetic energy, equivalents of potential energy, and equivalent of total energy in the quantum mechanics. So in classical mechanics, we have the equation for energy, which is kinetic energy plus potential energy plus equals total energy. But when we apply those operators for the quantum mechanics, we find uh, the equivalents uh, in the wave formation. In the quantum mechanics, we get the wave components by applying those operators here. So this is nothing but what we saw before, that we would have the psi function, the wave function. Now it depends on the x and t both. So we take partial derivative in one dimension with respect to x and respect to t, and we are applying the operator at the front. Here again, for energy, we applied the operator, but now we are taking in it with respect to t. Now, the wave function, of course, it includes both space and time dependence. Think about a wave. A wave is traveling, so it is traveling in x, and at any given time we want to see what is the. So we need to separate them out. So we solve the wave equation by looking at the dependence on time and looking at the dependence on the space. So by doing this, we have the Schrodinger wave equation in 3 dimension, where we get just the space dependence. So this del operator is what is called space operator. I wouldn't expect you to remember these equations, but the goal here is that I want to see what is Schrodinger wave equation and what do we achieve and how do we find the wave equation parameters. We talk about classical particle-based properties, but wave properties, how do we derive wave properties out of that? So this is the Schrodinger wave equation, where we have just the 3 dimensions. And let me see what's going on. So I've lost my mouse. And then this del operator is basically, which is shown here. At the lower level, which is double partial derivative of psi with respect to x plus double partial derivative of psi with respect to y and double partial derivative of the wave function with respect to z. And this is where then we can find the time dependence and the space dependence, and we can bring them together, and we get the both parts in there. And this is the equation 2-25 is what we get. So from this we can separate the time dependent and time independent variables equations out of that. So basically what we are getting is an equation which can tell us how things are moving in space and how things are moving in respect to time. Why do we want to separate these out? So many times we would have a problem where we may have a function which is just dependent on space. So in that case, where that would be time independent, and only space variables would be required. So we then solve the wave equation by using the time independent equation. Or there may be case where we are just we are looking at the time dependency. So in that case, we will use the time dependent equation. Now there are equations where when we apply an operator, we get a constant value out of it. So that kind of equation is called an eigenvalue equation, a proper equation where you get a proper constant as the solution of the equation. But many times we may have to just define arbitrary function, which would be a linear function of these eigenfunctions, these small proper functions, which would have their own weighing coefficients that would depend on the initial conditions. Now, without going into detail of the eigenfunctions, we have to see that